Good morning. All right, there we go. Hasn't it been an incredible meeting so far? So much good stuff. In fact, I want to, for those of you that are on social media, if you've learned something new, post it. Use the hashtag ADA 2023 and spread the word for those that are not here because they're missing something special. Let me poll you a little bit. I mentioned, at the opening remarks that this is the meeting around innovation. We've tried a lot of good new things and want to get your sense. So let me ask you about one of the things that we did for the first time, the opening plenary session. Who liked that? Excellent, excellent. So I think that's here to stay because we've been getting really great responses on that. So now it is a real pleasure for me to introduce our first speaker, Dr. Rodica Busui, a really distinguished physician, scientist, an incredible breadth of activity that I'll try to very briefly describe to you in a moment. She's also been an incredible mentor, and she is our 2023 President of Medicine and Science here at the ADA. At the University of Michigan, she holds a whole host of different roles. She is the Larry Soderquist Professor of Diabetes. She is the Vice Chair for Clinical Research and Outcomes in the Department of Medicine. She's also the Director of Clinical Research, Mentorship, and Development in the Caswell Diabetes Center. She's passionate about being a mentor, and you'll hear some of those stories. Really, she's done so much for so many people, and I know many of you are here in the audience to share this special moment with her. Her focus has been primarily around diabetes complications, but that's a wide area. So she's done work on diabetic neuropathy, on kidney disease, cardiovascular disease, foot disease, and amputation reduction. And then on top of all that, new technology and type 1 diabetes. So really breadth of knowledge and experience. She has been an investigator in almost every big landmark NIH study that one could name off. I'll just give you a few of those to give you a sense of this. So DCC EDIC, Barry 2D, the Accord trial, GRADE, one after another, really an incredible. These are the studies that really change the way we practice. She continues to be an endocrinologist where she sees patients, makes a big difference in their lives, but her contributions in science have been over 275 publications. She's also the chair of the NIDDK Foot Consortium that is really looking at how to bend the curve on amputations, a problem that is plaguing so many people in the world of diabetes. She's received awards from the Fulbright Foundation, from the American Diabetes Association, and from the University of Michigan. I'd like you to welcome our 2023 President of Medicine and Science, Dr. Rodica Busui.
Thank you, Bob. Thank you. Good morning. It is such an honor to share with you my professional journey, reflecting on where I started and how I have arrived today here addressing the leading diabetics scientific meeting in the world. I was born and grew up in Romania, a small country located in the Eastern Europe, with a very rich history and culture spanning for more than 2,000 years, and with beautiful landscapes flanked by the Danube River, the Carpathian Mountains, and the Black Sea. And with beautiful cities, picturesque cities, such as Timișoara, the city where I was born and where I attended medical school. As a child, and while growing up, I was fortunate to have amazing role models in my parents. My father Nicolae and my mother Elisabeta, who have constantly and by example taught my sister and I that by honest and hard work, one can achieve everything in life. My dream since childhood was to become a medical doctor. This dream started to materialize on a sunny September day. After a very competitive exam, I learned that I was admitted to the University of Medicine and Pharmacy Victor Babeș in Timișoara, placing second among more than 3,000 candidates competing for only 100 available slots. 6 years later, after rewarding preclinical and clinical rotations, I graduated summa cum laude and valedictorian of my class. Eventually, I entered internal medicine residency at the university hospital and then appointed assistant professor at the same university. But what really marked my journey was that by chance, I was assigned a rotation in internal medicine in the hospital wards and clinics, led by Professor Gheorghe Băcanu, a pioneer in diabetes care in Romania at the time, who had a vision to create a diabetes center and worked at the university hospital to provide a more standardized diabetes care. This was my first encounter with what people with diabetes had to struggle with. At that time, there were no glucometers or continuous glucose monitor. In fact, every morning before our rounds, it was our duty as students and early trainees to boil the urines of our patients to see whether there is glycosuria, to help dose their insulin. Nor were there any fancy insulin pumps or even single-use syringes. The extent of complications I witnessed during these earlier years were so devastating that it was a starting point in my career. My mind was set then, I will fight diabetes and help all people live a better life. I also realized that to accomplish my goal, I needed to engage on all fronts, combining transformative research that would lead to and enable a better care. And although in Romania there were very few resources at the time, I was so fortunate that with the fall of the communist regime, I was able to compete and be awarded a Fulbright fellowship. Thus, I took a rather big leap across the pond to pursue studies on the mechanism of diabetes and chronic complications. And I arrived in a very beautiful fall day at the University of Michigan campus in Ann Arbor to start my postdoctoral fellowship. These beautiful colors or the nice weather didn't last, and too soon a very harsh winter set in. And so my journey in the United States started as a postdoctoral fellow in the Division of Endocrinology and Metabolism at the University of Michigan. It was not easy. It presented many challenges, but even more opportunities, a truly upward journey, much like the Transfiguration Path of Romania. The endocrine division had an environment with a very rich tradition and track record in research in diabetes, diabetes complications, and diabetes care. It was recognized as one of the inaugural NIDDK-funded diabetes center. And I set to concentrate on one complication during my postdoctoral fellowship, diabetic neuropathy. It was a true puzzle due to the complex anatomy of the peripheral and autonomic nervous system and the progressive damage and loss of these nerve fibers, leading to sensory deficits in multiple organs and system dysfunction, with dramatic consequences on people's life, including amputations. I was assigned to work in the laboratory of Dr. Doug Green on bench research project using cell culture and animal models. I had no prior research training and no clue on what bench research really entails. In fact, I did not understand complex experiments sent in front of me, and I was really afraid to work with rats. And they sense it. Thus, not surprisingly, they beat me quite a few times at the beginning. But as Marie Curie once said, life is not easy for any of us. But we must have perseverance and, above all, confidence in ourselves. We must believe that we are gifted for something and that things must be attained. Still in my reserve, I grit my teeth and under Doug Green's steady mentorship, as well as of Martin Stevens, and with words of wisdom from Steve Fiennes, I set up to work on studies evaluating the role of oxidative stress and later inflammation in the development of diabetic neuropathy. I was rewarded as the data I generated were accepted by the American Diabetes Association as an oral presentation. This was my first oral presentation at an ADA annual scientific meeting in 1996 in San Francisco. It was a humbling and rather frightening experience, seeing myself presenting in front of a packed hall of scientists and clinicians from around the world. But this was another turning point which crystallized my determination to continue an academic career, as I believed that that was the best mechanism allowing me to help people with diabetes through both direct clinical care and engaging in transformative research that will improve their care. And here we are, 27 years later. I also knew that while research would remain an important part of my work, it had to be integrated into direct clinical care, which is my true passion. Thus, as with all foreign medical graduates in the United States, I had to embark on various examinations and training requirements, culminating with an endocrinology fellowship at the University of Michigan. And here I am with my fellow classmates at our fellowship graduation. During my endocrine fellowship, I also took the first steps in clinical research, concentrating on cardiovascular autonomic neuropathy and undertaking imaging studies involving the autonomic innervation of the heart, the primary extrinsic control mechanism regulating heart rate and cardiac performance. After graduating the fellowship, my journey continues. And I started my career as an independent investigator at the Formal Medical College of Ohio as an assistant professor in internal medicine and endocrinology. That is where I had my first lab, and I continued bench work linking oxidative stress inflammation and diabetic neuropathy, leading to my first independent NINDS funding and several publications. But it was at Toledo that I had another chance and opportunity, when our institution was selected to take part in the large landmark type 2 diabetes accord trial funded by NHLBI. Despite my very early career status, Dr. Sol Genut, a visionary in diabetes clinical research and leader in developing modern diabetes treatment, believed in me and selected me as site PI. Under his constant and kind mentorship, I've learned so much about the intricate ways of well-designed clinical trials and studies and how to successfully conduct them. I clearly remember his words of wisdom during the pilot phase of the accord, when many of us, myself included, expressed skepticism regarding the need for testing the intensive glycemia intervention. Sol said that one cannot assume something is right just because one may feel that way. We need to demonstrate it with strong evidence. I was also so fortunate to directly interact with and learn from other esteemed accord investigators, including Herzl Gernstein and Vivian Fonseca, who encouraged me to ask and evaluate new questions, enabling me later to lead a team of accord investigators across the United States and Canada to characterize the impact of cardiovascular autonomic neuropathy and other chronic complications in accord. As a result of my work, another dream comes true. I was recruited as an assistant professor in the Division of Metabolism, Endocrinology, and Diabetes at the University of Michigan. Go Blue! This was another turning point in my career, as I was actually prohibited by my new division chief to continue any bench research. Instead, I was asked to develop the clinical research program in diabetes and its complications. Thus, to paraphrase Churchill, to improve is to change, to be perfect is to change often. Back at Michigan, I was so fortunate to work with and have Dr. Eva Feldman as an unwavering mentor. Eva guided my steps in the research maze locally, across departments at Michigan. She also helped connect me with scientists nationally and internationally. Approximately a decade later, I had the honor of visiting together with Eva my medical school in Romania, where it all began for me. I set to work on the broad spectrum of diabetes complications, and I built a clinical research program at Michigan. And so my journey continues. I took the opportunity to leverage several landmark cohorts of people with type 1 and type 2 diabetes, of which I was an investigator, to learn important lessons for diabetes complications. While all these large studies have led to critical and broad evidence, I would like to highlight the memorable diabetes control and complication trial that officially was started 40 years ago. Here is the timeline. The DCCT study group presented its seminal findings 30 years ago at the American Diabetes Association scientific session in 1993 in Las Vegas, demonstrating that intensive glucose control effectively prevents retinopathy, nephropathy, and neuropathy in people with type 1 diabetes. These findings became a breaking news sent to all clinicians taking care of people with diabetes and changed the standard of care in diabetes in the United States and then worldwide. Ever since initiated in 1989, the American Diabetes Association Standards of Care quickly became the leading guidance document for clinicians managing diabetes throughout the world. DCCT findings unleashed an extensive domino effect, leading to an explosion of new insulins, new medications, new technologies, new management algorithms, new diabetes care policies, and so much more. And by the way, to quote Dr. David Nathan, to all our colleagues in pharma and industry, you are welcome. But the DCCT impact did not end in 1993. Its legacy continued through the EDIC follow-up as seen in this timeline. It had continued to unveil unparalleled evidence for the entire type 1 diabetes lifespan. And later today, here at the 2023 American Diabetes Association scientific session in San Diego, the DCCT EDIC Research Corps will highlight 40 years of discovery that I urge you all to attend. The DCCT has been an important part and catalyst of my own career through continuous mentorship and support from Dr. Sol Genuth and David Nathan, who welcomed me as a part of the research group family and enabled me to explore so many new avenues studying the natural history of chronic complications. For instance, working with Dr. Barbara Braffett, John Lakin, and other DCCT-ED colleagues, we demonstrated a progressive increase in the prevalence of diabetic peripheral and cardiovascular autonomic neuropathy during 30 years of follow-up, despite changes in standard of care. I have extended these studies on phenotyping neuropathy using validated instruments such as the Michigan Neuropathy Screening Instrument in many other cohorts. And here, working with my younger colleague and mentee, Dr. Kara Mizokami-Stout, and with support from our colleague, Dr. Roy Beck at the DCC, we assessed both diabetic peripheral and autonomic neuropathy in this large contemporary T1D exchange cohort throughout the entire United States, managed based on current standards and practices. I have also done research in contemporary cohorts with type 2 diabetes, such as the addition study when I had the opportunity to work with our Danish colleagues on the left and with my colleagues in the GRADE cohort on the right, unveiling very high prevalence and incidence rates of peripheral and cardiovascular autonomic neuropathy in these participants with type 2 diabetes on both sides of the Atlantic. Having the opportunity to study chronic complications in youth with type 1 and type 2 diabetes together with our colleagues in the search study group has unfortunately unveiled unexpectedly high rates of chronic complications, particularly in youth with type 2 diabetes. Such data and other emerging evidence has prompted the American Diabetes Association to select youth with type 2 diabetes as one of the 2023 research funding priority. Unfortunately, the advances for finding effective disease-modifying therapy to stop the consequences of neuropathy remain slim. Thus, our lessons continue. I have pursued studies to understand critical risk factors. For instance, our study in DCCT-ED cohort identified differences between traditional risk factors between peripheral and cardiovascular autonomic neuropathy. And more recently, I have engaged in evaluating non-traditional risk factors, including the emerging social determinants of health for diabetic neuropathies. As highlighted by our studies with my mentees, Dr. Kara Mizokami-Stout and Lin Ang in the T1D exchange cohort, several social determinants of health such as education, access to care and insurance, or income, as well as several psychological factors were associated with high risk of developing peripheral and autonomic neuropathy. With my colleagues in DCCT-EDIC, we also found that the benefits of early intensive glucose control to effectively prevent the development of neuropathy in type 1 diabetes continue during EDIC for up to 14 years, conclusively demonstrating that metabolic memory applies for CAN and DPN. While with my colleagues in the large Berry 2D trials, we found that the insulin sensitizer strategy significantly reduced the incidence of peripheral neuropathy in people with type 2 diabetes and confirmed coronary artery disease. Furthermore, with Dr. Doria, Tan, and many other ACCORD investigators, we unveiled that intensive glucose and blood pressure intervention significantly prevented cardiovascular autonomic neuropathy in people with type 2 diabetes ACCORD participants. However, as highlighted here, the complexity of linked mechanisms and downstream pathways proved to be important challenges for disease modification. Many of these share common pathogenic mechanisms that involves modification to neuroimmune interaction mediated by inflammatory signals. Thus, working closely with my close collaborator and friend, Dr. Eva Feldman and her laboratory, gene expression profiling studies of human nerve biopsies identified several key targets linking lipid metabolism and inflammatory response, including through the NF-kappa B pathway, effectively connecting clinical and bench research. We have leveraged this finding through my work with Alison Goldfein in the Tinsel T2D trial and designed initially a pilot trial targeting this pathway with an old drug in people with mild and moderate neuropathy, findings that led to the successful funding of a phase 2 clinical trial by NIDDK with Eva and me as PIs. In parallel, I continued studies in understanding mechanism and impact of cardiovascular autonomic neuropathy. And I was so fortunate to be awarded my first clinical research grant by the American Diabetes Association, marking another turning point in my career. As in my case, ADA funding has helped launch so many careers, and I know that many of you are here in this room. The funding from ADA was essential for studying molecular mechanism of cardiovascular autonomic neuropathy, and then the role of cardiovascular autonomic neuropathy in the development of myocardial dysfunction in diabetes. And this initial generated data from pilot study were validated in the entire DCCT-ED cohort, all leading to my first clinical R01 funded by NHLBI. Working with a team, colleagues from cardiology, nephrology, radiology, we identified distinct metabolic signature in the TCA cycle and the amino acid metabolites that were associated with cardiovascular autonomic neuropathy and left ventricular dysfunction progression. Studies that have later contributed to establish the role of metabolic dysfunction and cardiovascular autonomic neuropathy as mechanism of heart failure in people with diabetes. While in parallel, I continue studies that unveil the impact of CAN as an independent predictor of cardiovascular death and other major cardiovascular disease events in both people with type 2 diabetes in the accord on the left and people with type 1 diabetes in DCCT-ED on the right. In the meantime, emerging data raise the question that the risk for developing diabetes complications may be different in women with diabetes compared with men. And although the time does not permit to review them all, I will highlight several reports from large observational cohorts indicating that after adjusting for demographics, women with diabetes had a 4 to 5-fold higher risk for fatal coronary artery disease as seen here on the left, and a significantly higher risk for heart failure hospitalization as seen here on the right compared with men. In our own mechanistic studies, we observed that women with diabetes had significantly lower myocardial efficiency compared with men, implying earlier metabolic and energy deficits in the myocardium of women with diabetes. And most recently, our studies led by Dr. Barbara Braffett and Sam Dagogo-Jack found that despite that women with type 1 diabetes had a less atherogenic risk profile, the rate of cardiovascular disease events was the same as in men, raising the question of whether there is a heterogeneity in biological risk or the clinical care of women with diabetes may be neglected at the point of care. Thus, our team at Michigan, with funding from JDRF, embarked on a quest to unveil factors driving such a risk heterogeneity. And I am so happy to announce that the American Diabetes Association has selected improving the health of women with diabetes across the entire lifespan as one of the other 2023 main research funding priority, a long neglected subject so close to my heart. And now I would like to let a remarkable woman, diagnosed with diabetes as a youth, to share some of her thoughts.
My journey with type 1 diabetes began 46 years ago. During my first year in living with diabetes, I attended Camp Medalia in Michigan, which was my introduction to the wonderful services provided by the American Diabetes Association. In 1985, I had the opportunity to attend a National Youth Leadership Congress with the ADA that was held in Washington, D.C. It was through this amazing program that I learned that I was very behind in how I was managing my diabetes. Not only has the ADA provided me with many resources and leadership opportunities, but it connected me to extraordinary diabetes specialists like Davida Kruger and Dr. Rodica Pop Busui. I am extremely grateful for their compassion and expertise which enabled me to be included in numerous life-changing clinical trials. I am a healthy wife, a mother of 2 successful sons, a pharmacist, and a certified diabetes educator. I truly admire and greatly appreciate Dr. Rodica Pop Busui, the American Diabetes Association, and all of the outstanding advocates who give unselfishly to improve the lives of people with diabetes. Thank you.
Thank you, Susanna. In my journey, another area of research and care involves diabetes foot complications that unfortunately, as you have heard also this morning, continue to lead to unacceptable high rates of amputations among people with diabetes in the United States and many other countries around the world. At Michigan, we built a team of investigators spanning a broad spectrum of expertise on diabetes foot complication, including podiatrists, endocrinologists, vascular surgeon. And we demonstrated the effectiveness of this teamwork for clinical care by reducing amputation in our health system by 60%. And that also poised us to deliver effective care during the pandemic. We are so proud to be part of the first ever Diabetes Foot Consortium funded by NIDDK that aims to identify and validate biomarkers predicting diabetic foot ulcers healing that could be implemented at the point of care. And you've heard this morning some of our initial discoveries. This consortium was recently renewed for a new cycle, which I was elected to chair, and I would really like to acknowledge the support from NIDDK, particularly Dr. Teresa Jones, Yan Lee, and Will Cephalou for this critical initiative. Thus, whether through state-of-the-art NIDDK funding research or through the new American Diabetes Association priority that launched the Amputation Prevention Alliance to provide better education and resources to clinicians, people with diabetes and their family, or through effectively lobbying and advocating policymakers, we are now fighting amputations on all fronts, and we will be saving more than 84,000 limbs every year moving forward. Being so fortunate to have had outstanding mentors, I set myself to give back, to mentor and help build a new strong generation of successful investigators at Michigan and outside. Among all, here are just few of remarkable young colleagues: Dr. Lin Eng, Kara Mizokami-Stout, Alex Lin, Brian Schmidt, and Salim Hayek, that allowed me the honor to mentor them towards their independent funding and recognition. And here is my mentee, Kara, who wanted to share some of her thoughts.
Growing up in rural southern Colorado, many of my loved ones and friends were affected by type 2 diabetes and suffered from end-stage complications due to poor access to healthcare. During college, I also met my now husband, who has had type 1 diabetes since the age of 8. And these early exposures fueled my passion for caring for those with diabetes. After undergrad, I therefore attended medical school and internal medicine residency, knowing that I wanted to be an endocrinologist, but as a first-generation physician, the thought of a career in academia seemed daunting and frankly unobtainable. And then in 2015, I moved to snowy Ann Arbor, Michigan for endocrinology fellowship. And while here at the University of Michigan, I had the great fortune of meeting Dr. Rodica Busui. And she not only took me under her wing as a mentee, but completely changed the course of my life. I've always been impressed by her ability to lead by example. Her tireless dedication to her patients is matched only by her determination to end diabetes complications through research and implementation of evidence-based diabetes care. And as a mentor, she is extraordinarily generous with her time, feedback, resources, and encouragement. And I often feel that her confidence in me is unwarranted, but I'm so very grateful for her as a mentor and a friend. I can unequivocally say that without her supports, I would not have considered the possibility of an academic research career. Rodica, thank you so much for being such a wonderful doctor, mentor, and a friend. And congratulations on your successful ADA presidency. I certainly cannot think of anyone more deserving of this honor than you.
Thank you. Thank you, Cara. Okay. Mentoring and building a new generation of successful investigators had been also a priority of the ADA through continuous funding of career development awards for so many investigators, many of whom are here in this room, and more recently through the Cutting Edge Pathway to Stop Diabetes, the program that has currently 16 active pathways awardee, with the 2 newly minted one in 2023 that you've heard from in our first day in opening session. My journey and work was intertwined so closely and at so many levels with the American Diabetes Association, starting with that first presentation that led to countless plenary presentations, from receiving critical grant funding from the ADA, to participating and leading grant review committee, and having the honor to serve the American Diabetes Association in many capacities, including planning scientific session, participating in shaping the standards of care, the research policies, and more recently in leadership and advocacy. Among this, I'd also like to highlight that I was honored to be tasked by the ADA to chair the American Diabetes position statement in neuropathy, leading a group of investigators most experienced across both cross of the Atlantic with my good friend, Professor Andrew Bolton. We work as a unified team to critically review the evidence and provide evidence-based guidance for clinicians and people with diabetes. And we recently updated this to provide the guidance for treating the challenging neuropathic pain while strongly fighting opioids on all fronts. Leading the cardiovascular disease interest group of the American Diabetes Association, we had the opportunity to promote programs for the advancement of cardiovascular disease research implementation and work with the American Diabetes Association, American Heart Association, Know Diabetes by Heart. And most recently, I was honored to chair a group of endocrinologists, cardiologists, nephrologists, and primary care physicians to finalize the American Diabetes Association consensus on heart failure in diabetes. Our consensus, endorsed by the American College of Cardiology, provides guidance to all clinicians on how to best detect, monitor, and manage from the earliest stages people with diabetes and heart failure, which is now the most prevalent cardiovascular complication in diabetes. Before I end, I would like to acknowledge that in my journey, I was so fortunate to be mentored by and work with phenomenal people. To all of you, and to the funding agencies, and to all people with diabetes, a heartfelt thank you. But a vital key to my success was my family continuous love. My parents, my sister Anka, who is here in the front row, my brother-in-law Mircea, my nephew Victor, our daughter Ellie, and son-in-law Kyle, my adopted Ann Arbor family, Marina, Lara, and John, and now our grandchildren Ansel and Ada. But most importantly, the unwavering support and unconditional love of my brilliant husband Don, with whom I shared life journey, whether it be on the ski slope, visiting amazing places, or preparing dinner in the kitchen after a long day at work. Thank you very much. Thank you. Thank you. And now, it is truly my pleasure to introduce you to my friend and colleague, Dr. Matthias Zschöp. Dr. Zschöp is the Alexander von Humboldt Professor at the Technical University Munich and CEO of Helmholtz Munich and Vice President of the German Helmholtz Association. He began his career with an interest in obesity, which inspired his devotion to finding a cure for obesity. In 2000, he identified ghrelin as the first and only circulating hunger hormone. Based on studies of ghrelin, gut hormones, and brain circuits, Zschöp and his long-term chemistry collaborator, Richard DiMarchi, hypothesized that integrated action of specific hormones might provide safe and unprecedented weight lowering to reverse obesity. They pioneered a series of single molecule therapeutics which simultaneously activate 2 or more hormone receptors to achieve unprecedented body weight, glucose, and lipids lowering. This novel form of dual and triple hormone pharmacology includes agonists to GIP, GLP-1, and glucagon receptors. Multiple representatives of the new drug class Zschöp and DiMarchi discovered are successfully advancing in clinical trials, and the first approved FDA is the dual GIP-GLP-1 co-agonist tirzepatide. Its ability to overcome human obesity validates the virtue of integrated combinatorial pharmacology, and it reaches efficacy comparable to gastric bypass surgery. Please welcome the 2023 Banting Award winner, Dr. Matthias Zschöp.
Dear President Busui, dear colleagues and friends, ladies and gentlemen, it is impossible to describe the feeling now following in the footsteps of the colleagues who have been recognized with the Banting Medal and who have been my role models ever since I started getting involved in research. Ron Kahn and Jeff Flyer, Barbara Kahn, Bruce Spiegelman, Jerry Schulman, Francis Ashcroft, Mimo Achille, Steve O'Reilly, Jens Holst, Phil Scherer. What an honor to be standing here today. But some of you may remember that we sort of have been here before. Exactly 12 years ago in 2011, at the ADA annual meeting here in San Diego, back then on the occasion of the Outstanding Scientific Achievement Award. 2011. Wow. Our world has changed so much since then. I mean, in 2011, Joe Biden was in the White House. Tom Cruise was coming out with a new Mission Impossible movie. LeBron James was in the NBA playoffs, and the pop charts were ruled by a certain Taylor Swift. And I was standing here telling you about how dual and triple gut hormone agonists could control obesity and prevent diabetes in the future. You know what else hasn't really changed though? The diabetes pandemic is still here and still growing. In spite of all the research, in spite of the numerous scientific advances bringing improvements to patients' lives over the last 100 years, since Frederick Banting and colleagues discovered insulin, we have not managed to control, reverse, or prevent type 2 diabetes worldwide. When I started as a young physician 30 years ago at the endocrine division at Munich University Medicine, I, like many of my colleagues, struggled with that question. Could there indeed be any way to actually stop or even reverse the diabetes pandemic? One major driver of diabetes incidence has certainly always been another pandemic, that of obesity. Now, the many experts in this audience may not agree on the specific molecular mechanism that leads from obesity to type 2 diabetes, but I'm pretty certain the vast majority of you would agree that if we could remove obesity as an epidemiological driver, for example by pharmacologically normalizing and controlling body weight, we could reverse the diabetes pandemic and save tens of millions of lives, as diabetes isn't the only consequence or complication of obesity. which also decreases life expectancy by promoting cardiovascular disease, neurodegeneration, or cancer. Now, back then, 30 years ago, there were simply no effective anti-obesity drugs. No pharmacology existed that would allow it to safely reduce body weight by more than 5% or so. Blessed with equal amounts of naivete and enthusiasm, I decided that that was what I wanted to dedicate my career to. Discovering novel kinds of drugs that would safely reduce body weight by 20, maybe 30%. That would enable us to control obesity and prevent diabetes. But how? Since this was considered to be absolutely impossible at the time. Well, then something happened. Jeff Friedman at Rockefeller University discovered the first molecule and the first physiological signal that really controlled body weight, leptin. Leptin is produced and secreted by adipose tissue and acts in the brain to promote satiety and regulate fat mass. Even though it emerged shortly thereafter that leptin wasn't going to be the solution for the obesity pandemic, as obese individuals were resistant to leptin action, Jeff's transformative discovery made me decide to leave clinical medicine and go into research. Starting with a 3-year fellowship at Eli Lilly Research Labs, where I wanted to learn more about the drug discovery process. During that time, my mentor Mark Hyman and I discovered that there actually was an endogenous leptin opponent, a peptide from the stomach called ghrelin that functions as a hunger hormone and increases body weight. However, blocking ghrelin also didn't suffice to control obesity, and I started to conclude that interfering with one signaling pathway at a time just wasn't going to be enough. Still, the discovery of the satiety and hunger signals leptin and ghrelin taught us something important. Both almost exclusively acted in the brain to exert their effects. An observation which fit with the insights into human genetics provided, for example, by Giles Yeo and Steve O'Reilly, who were first to show an important body weight controlling function for the melanocortin 4 receptors in the brain. From this perspective, human obesity started to emerge sort of like a brain disease. What did that mean for the mission to discover highly efficient obesity therapeutics? And looking back today, it may not have been the discovery of the hunger hormone that made my postdoc fellowship a success, but it was meeting my colleague, friend, and long-term cooperation partner, Richard DiMarchi, during the time. Richard is one of the worldwide leading peptide chemists, and we quickly found out that we shared the vision of finding highly efficient therapeutics for obesity, and he brought a lifetime of experience on how to make actual drugs into the collaboration. Both of us then left the pharmaceutical industry, returned to academia, Richard to Indiana University, myself to University of Cincinnati, and started working together as a joint operation across disciplines, combining physiology, biology, chemistry, and pharmacology toward one common goal: discovering drugs that allows safe and effective body weight loss of 20 or maybe even 30%. Today, Richard and I have been leading joint research for 2 decades, and it is obvious that neither one of us would have been successful if we would have embarked on this mission separately. Therefore, I would like to share this honor today officially with Richard DiMarchi. Now, we together assembled a clear strategy. First, we both were convinced that multiple receptors had to be targeted. Second, a sufficiently specific direct targeting of brain circuits to exclusively control body weight using pharmacology wasn't and still isn't possible. We decided to work on the basis of natural gastrointestinal hormones, which are naturally designed to specifically act on brain circuits controlling body weight and metabolism. And third, with that, the core of our strategy emerged that multiple human gut hormone receptors in the brain had to be activated at the same time, preferably using a single molecule approach to avoid challenges with testing, mixing, stabilizing cocktails of molecules and such. In the meantime, rapidly advancing research had identified numerous gut hormones and gastrointestinal factors with influence on metabolism. Finding the right combinations proved difficult, as making novel, soluble, and stable receptor agonists, purifying and repeatedly testing them in vitro in cell-based assays and in disease models is just very labor-intensive and takes months, if not years, for every pathway that is being targeted. We investigated dozens of single combinations, but also took some guidance from insights into the molecular basis of bariatric surgery benefits, ending up with a strong focus on the glucagon peptide family. Now, of course, the textbook version of glucagon was that this hormone mostly does one thing. It increases blood glucose. Therefore, not surprisingly at the time, programs ongoing in the pharmaceutical industry were all aiming to block glucagon receptors. We took a different approach. We aimed for activating glucagon receptors in order to generate better therapeutics for obesity and diabetes. We were called crazy more than once, and we were told we would be damaging our academic reputation if we continued to pursue this. We remained determined, though, as we had already zoomed in on lesser-known actions of glucagon, described in mostly forgotten literature, including how glucagon can help burn calories, drive lipolysis, or promote satiety. Importantly, also the fact that glucagon receptors in liver cells allow to improve blood lipids and clear liver fat. In addition, Richard saw opportunity in the chemical and structural properties of glucagon and its peptide family that might allow engineering of hybrid hormones with synergistically maximized efficacy. Our first step was to generate glucagon receptor agonists that would serve as better tools to test pharmacological hypotheses, meaning they'd have to offer longer half-life, improved solubility, comparable affinity at human and mouse receptors, and remain full specificity. One of the chemical optimizations included in the process was the addition of the so-called CEX tail to glucagon to improve half-life of the molecule. A lesson learned from the heloderma lizard that you can see here on the left side. Our preclinical studies with these molecules led us to the first eureka moment. Glucagon receptor activation in diet-induced obese mice successfully caused more than 20% weight loss, comparable with preclinical exendin, but with an entirely new mechanism. That reassured our hopes for the possibility of synergistic combination. And it triggered a paradigm change for the field, that it is not glucagon receptor antagonism, but agonism that offers relevant potential for the treatment of obesity. It was indeed possible to integrate glucagon receptor agonism benefits into one molecule or not. With another system, we weren't sure. But we thought it might be possible with a GLP-1 receptor agonism in combination. Could we indeed show that a unimolecular dual agonist would bring additional benefits? Well, with Richard's chemistry, we could. A series of long-acting glucagon receptor and GLP-1 receptor dual agonists was made and validated, and we tested those once weekly injections in diet-induced obese insulin-resistant mice. The result was stunning. The more glucagon receptor action engineered into the molecules, the more effect we saw. Overall decreasing body weight 20 to 30%, a major breakthrough not previously seen. We still had to show, though, that glucose and insulin levels were not deteriorated. After all, we did activate glucagon receptors. Our hope was that the weight loss along with the GLP-1 receptor-mediated metabolic benefits would sufficiently buffer the diabetogenic liability of the glucagon system. And it worked. Glucose tolerance as well as insulin secretion markedly improved, even though we were activating glucagon receptors. This was very encouraging, almost too good to be true. So reviewers were understandably asking, did we maybe just coincidentally make a super strong version of a GLP-1 receptor agonist? Was there even anything beyond GLP action in these molecules that contributed to the impressive benefits? We used a genetically engineered mouse model that didn't have any GLP-1 receptors to test that. We still saw that the effects on body weight and body fat were there, and again, the more glucagon action was engineered into the molecule, the more benefits were achieved. So yes, this indeed was a functional dual agonist. Well, today, almost 15 years after our discovery of the first dual agonist, which we published in Nature Chemical Biology in 2009, several versions of such glucagon GLP receptor dual agonists are moving through clinical trials. The first example was the dual agonist cotadutide by AstraZeneca Medimmune, which validated body weight and blood sugar effects in clinical trials, but also confirmed that glucagon receptor activation, likely due to presence on liver cells where GLP-1 receptors are not expressed, is bringing additional benefits in terms of blood lipids, which is positioning dual agonists containing glucagon receptor activation is promising for treatment of fatty liver disease. There are other promising representatives of that drug class. Here's another one, a dual agonist by Boehringer Ingelheim, phase 2 clinical trials showing 18% weight loss and obesity along with glucose improvement, etc. And a lot of the patients actually achieve more than 20% weight loss with that dual agonist. These data just came out yesterday. Overall, our discovery of the first dual agonists added a new class of therapeutics capable of superior anti-obesity effects combined with significant glucose and lipid improvements. Encouraged by this success, validating our concept of single-molecule multi-receptor drugs, we decided to push further and explore other combinations. We next zeroed in on another, as we believed, misunderstood and understudied hormone, the glucose-dependent insulinotropic peptide GIP. And again, similar to glucagon, the entire research field was believing that if GIP receptors were a relevant target at all, they had to be antagonized or blocked. Richard and I chose the opposite approach. Our vision was to activate GIP receptors, specifically in the brain, to promote satiety, improve metabolism, and achieve significant weight loss. We were convinced that activating GIP receptors could be another powerful way to decrease weight loss, to increase weight loss and obesity. But we were clearly the only ones at the time. Everywhere else in academia, as well as industry, the search was ongoing for GIP receptor antagonists. We stayed the course. Our first step again was the design, synthesis, and validation of a series of stable, long-acting, soluble, specific, and effective receptor agonists. Multiple molecules were made for this first set of receptor agonists and always tested for activity in the mouse and human receptors to make sure they were as translationally relevant as they were mechanistic research tools. The most balanced and best performing GIP receptor agonists were then tested in preclinical models for their in vivo activity. And once we observed the expected incretin effect on blood glucose, you see here, we used mouse models that were genetically engineered to lack the GIP receptor to make sure that the effect was specific and therefore indeed disappeared in their GIP receptor knockout mouse, as you can see here on the right side. But the million-dollar question was, what would happen with body weight if GIP receptors were activated lastingly with highly effective and long-acting agonists? We found that indeed, long-term GIP receptor activation would cause substantial loss of body weight, mostly body fat. As this was going against the accepted paradigm, we repeated this with several compounds and study designs, and then again made sure that the effect we saw was mediated by the correct receptor. Indeed, the GIP receptor agonist still caused weight loss in mice missing the GLP-1 receptor, but not causing any weight loss in mice genetically engineered to miss the GIP receptor. By now, this concept has been validated in humans. Results from clinical studies by Eli Lilly disclosed yesterday here at this meeting showed that indeed long-term activation of GIP receptors causes dose-dependent weight loss in humans. Now, while this was reassuring that our vision seemed to be correct and the GIP signaling, similar to glucagon signaling, may have been misunderstood in the past, we still had to go the next step and integrate the novel weight loss mechanisms into a single molecule with at least one other signal to achieve another dual agonist. We again chose GLP-1 as a partner with the intention of creating a powerful dual incretin or twincretin that would maximize beneficial effects on satiety, energy balance, and glucose metabolism. First preclinical experiments testing co-administration of longer-acting GIP and GLP monoagonists revealed potential for this combination as weight loss was most prominent with simultaneous administration of both agonists, GIP here being sub-threshold. It was our ambition to again come up with a single molecule that would be able to activate both receptors and not require a mixture of two compounds into some cocktail or two-chamber systems for injection. It took some time and took hard work, but Richard and his team succeeded in making the first single molecule dual agonists for human GIP and GLP-1 receptors as proven in vitro, which we then tested in our preclinical obese and insulin-resistant mouse models. Significantly and dose-dependently, their body weight was decreased by almost 20% in as little as 1 week. Another potent class of anti-obesity drugs was discovered, again based on the principle of activating multiple receptors. While our work on the dual agonist GIP-GLP-1 had started almost 20 years ago, we first published the discovery of this drug class of dual incretins in 2013 in Science Translational Medicine a decade ago. We then collaborated with Roche Pharmaceuticals and Novo Nordisk to test this approach in a short clinical phase 1b study, where we could confirm benefits on blood glucose and body weight, as you can see in this post-hoc analysis. Now, this was a very short study of a few weeks, where curves just started to differentiate, and compound optimizations available today, such as diacid modifications, were not yet available. More advanced versions of this drug class of GIP-GLP receptor coagonists then were generated, such as Eli Lilly's tirzepatide or Mounjaro, which is the first dual agonist to be approved by the FDA for diabetes. Even though now only approved for diabetes treatment, the game-changing breakthrough, in my mind, associated with this dual agonist is its body weight effect in obesity, where this GIP receptor, GLP-1 receptor coagonist, on average achieves 22.5% weight loss, an effect believed to be absolutely impossible not long ago. Now, it has been communicated at this and other meetings, tirzepatide not only is optimized for longer half-life, it is also balanced toward GIP, the ratio of about 5:1 between activation of the human GIP versus the human GLP-1 receptor, which may contribute to its efficacy. What's even more impressive is the weight loss effect of this dual agonist in patients with diabetes. In patients with diabetes, monoagonists do hardly achieve 10% weight loss, but the dual GIP-GLP receptor agonist still achieves an average of about 15%. While the anti-obesity effect certainly represents the transformative game changer, the effect on blood glucose is impressive. Tirzepatide achieves up to 2.6% decrease of HbA1c in the SURPASS and SURMOUNT trials. Now, one thing Richard and I had always been warned about was potentially serious side effects of dual agonists. We knew the GLP-1 receptor activation is associated with side effects such as nausea and vomiting. Of course, that could have been something to worry about with our dual GIP-GLP agonists. After all, we're including yet another incretin. Our hope was that we would reduce likelihood and seriousness of side effects as we'd reduce receptor occupancy for each single system and take away pressure from the GLP-1 receptor system. Indeed, in spite of significantly increased efficacy, side effects of the dual agonist, like tirzepatide, are not exceeding those of an optimized monoagonist, as shown here. As a matter of fact, the addition of GIP receptor activation may have something to do with that. Elegant studies by Matt Hayes and colleagues have shown recently that activation of the GIP receptors actually don't have that emesis and nausea effect, but can powerfully reduce the nausea and emesis caused by GLP-1 receptor activation, as you see on the right side. Another aspect with GIP, the long overlooked gut hormone, which is the dominant part of tirzepatide, may play a critical role for the powerful performance of dual agonists. That may not only be true for achieving major body weight loss and reducing side effects, as was shown in a series of recently published studies, studies led by John Campbell and Timo Müller from our institute, John Campbell from Duke, in collaboration with scientists at Eli Lilly and Novo Nordisk. And it was shown here in human pancreatic islands that the dual GIP-GLP-1 receptor agonist tirzepatide requires the GIP receptor for beneficial effects on insulin secretion, much more so than the GLP-1 receptor. That means not only is it real agonism at the GIP receptor that's at work here in human tissue, but again, GIP may be a key component of the unprecedented efficacy of these dual agonists. This is what we had hypothesized 15 years ago, and I had shared with you on the stage 12 years ago. Now, there have been preclinical data from knockout mice of the GIP receptor and from infusion of natural GIP with its short half-life that would have suggested a receptor antagonist may be what's needed. Now, indeed, endogenously secreted GIP, which has a very short half-life, may only reach peripheral targets, such as, for example, adipose tissue, where it likely has mildly obesogenic effects. That endogenously secreted GIP will not reach the brain. This is very unlikely given the instability of endogenous GIP. This means an antagonist or a genetic knockout would indeed also result in some weight loss, but based on the removing of the peripheral GIP effects. Now that is entirely different from the situation where stable and optimized dual agonists are being injected. These will reach and activate GIP receptors in the brain, where they synergize with GLP-1 receptors to powerfully promote satiety and weight loss. That the GIP receptors in the brain indeed play a key role for the superior efficacy of dual agonists, we were able to prove in studies led by Timo Müller, who used mice he genetically engineered to remove the GIP receptors from the central nervous system. He then showed that dual agonists lost their superior body weight loss effects over monoagonists in the knockouts. Timo, who had been a fellow in the lab, then group leader and now institute director with Helmholtz and full professor at Munich University, is pushing this further. He and his team just showed in studies currently in review that surprisingly, leptin receptor carrying neurons, such as hypothalamic AGRP neurons, have little if anything to do with this. He genetically removed GIP receptors from CNS neurons expressing the leptin receptor, and in those mice, dual agonism still works perfectly well and superior to GLP-1 receptor monoagonism. So which neurons really are the primary target? Again, Timo and his team at Helmholtz Munich may just have identified them. He finds that a very specific subpopulation of GIP receptors in the brainstem neurons is being activated by GIP receptor agonists. And when he removes those receptors genetically, GIP loses its ability to decrease food intake and body weight. This may be the switch which turbocharges action of highly efficient anti-obesity dual agonists. While the exact molecular underpinnings will sure be deciphered for years to come, it is clear at this point that dual agonism at GIP and GLP receptors outperforms monoagonism preclinically and clinically regarding body weight and blood glucose effects. The entirety of currently available clinical data is making it at this point likely that multi-receptor therapeutics will become the primary therapeutic solution for human obesity. Now, with two different dual agonists being so successful, we of course had started, actually already 15 years ago, to experiment with the idea of a triple agonist capable of activating the GIP, the GLP, and the glucagon receptor. Again, I had shared this vision with you on this stage 12 years ago. We started with co-administrating glucagon receptor agonists with the dual GIP-GLP receptor agonists and observed massive additional weight loss benefits. These types of studies in our mind validated the principle and convinced us that it was indeed worth going after a single molecule capable of activating all three receptors. The question was if that was even possible, and if yes, in which ratio should these three components be present? This triggered years of discovery research, again driven by Richard and his chemistry team, work that sort of resembled solving a Rubik's Cube, hoping to find combinations of amino acids that would generate optimal balance and maximally beneficial action profile, without altering the natural hormone too much and then risking increased antigenicity. What you see here is, of course, still highly simplified. The real structure looks more like this, as Richard and his team again succeeded in making the first single molecule therapeutic capable of activating three human gut hormone receptors. One important strategic consideration was that glucagon would now be buffered by two incretins, increasing chances diabetogenic liabilities could be neutralized. Now, when we tested these first versions of triple agonists, we were not disappointed. They showed unprecedented beneficial effects on body weight, food intake, and metabolism. The purple graph is a dual GIP-GLP agonist, similar to sort of tirzepatide. The more reddish one is a triagonist, achieving almost twice the body weight loss in preclinical models of obesity. That does translate into loss of fat mass, improved cholesterol, and greatly decreased glucose and insulin levels, even though glucagon receptor agonism had been engineered into the dual agonist molecule to make it a triple agonist. After many years of work, the discovery of the drug class of triple receptor agonists was published in Nature Medicine in 2015, and since then has also been translated into human application. Again, spearheaded by Eli Lilly and Company, a first triagonist has been tested in human obesity in phase 1b. Phase 1b data suggests that not only it is very potent in decreasing body weight, but it may be indeed superior to or even tirzepatide Mounjaro, based on comparison with similar trials of that compound. Now, phase 2 trials of the triagonist have already been performed. We're all eagerly awaiting tomorrow's session where these data will be disclosed. Now, our own lab has in the meantime continued to investigate the molecular underpinnings of multi-receptor drugs, including the triple agonists. And here are some very recent, unpublished data from our lab, spearheaded by Aaron Novikov and Alberto Serrano, who used CRISPR-Cas technology to generate the first triple GIP, GLP, glucagon receptor knockout mouse model, as we wanted to find out if triple agonists just happen to do anything beyond activating these three receptors to achieve the really unprecedented weight loss benefits. We then administered triagonist in wild-type littermate control mice and in triple receptor knockout mice, and we found, when the next slide comes, and we found that there is no effect in mice lacking all three receptors, showing that there are no coincidental off-target effects. The benefits really are a consequence of the activation of all three receptors. Summarizing this part, our discovery of triple receptor agonists established yet another class of novel therapeutics, which at least preclinically, and as it seems clinically, may outperform mono and dual agonists as highly effective obesity drugs. Of course, there are numerous other multi-receptor drugs now being tested. This is already outdated, sort of daily changes, at least a dozen in clinical trials, a couple more on the horizon. Some of these drugs have the potential to transform metabolic medicine by overcoming, reversing the obesity epidemic. Alone, the already available data show how dual agonists are approaching the efficacy of gastric bypass surgery. We will find out tomorrow if, as suggested by preclinical and early clinical data, maybe triagonists will be capable of weight loss of more than 20% in phase 2 trials, with a potential trajectory pointing toward even 30% weight loss in phase 3 trials. Let's see. Let me conclude with the take-home message that, against all expectations, 3 decades of work resulted in the discovery of the new drug classes of multi-receptor drugs that are likely offering patients and physicians, for the first time, medicines capable of controlling obesity, similar to how in the past beta blockers and ACE inhibitors have made it possible to control blood pressure. By getting obesity under control, dual and triple agonists, based on what we know today, and if broadly available and hopefully sufficiently affordable, also have the potential to slow down, if not reverse, the diabetes pandemic. There is so much more to be done. Richard and I are convinced that beyond principal control of obesity, yet another generation of even more sophisticated therapeutics can offer a metabolic precision medicine of the future, tailored to the needs to specific subpopulation of patients. We are therefore working on advancing several dual agonists designed for cell-specific delivery of small molecules toward clinical application based on principles that may be applicable to diseases beyond obesity and diabetes. With such a pool of next-generation therapeutics, a metabolic precision medicine of the future may become possible. Well, speaking of the next generation, this all was and is the work of a great team, and one of the key scientists of the team is Timo Müller, who you see here pursuing his real passion. All right, which is hanging out with super dangerous predators. This is not Timo Müller, by the way. This is Timo Müller. That is not that dissimilar to Brian Finnan, another key scientist of the team who trained as a grad student in chemistry with Richard before he moved to Munich to work with us at the Helmholtz, before he then moved on to join Novo Nordisk, where he is now vice president of obesity. He's seen here pursuing one of his hobbies, running with the bulls in Pamplona. Of course, any claim that working in the DeMarchi Chirp labs requires risk-taking levels close to a death wish are baseless or at least vastly exaggerated. I am deeply grateful to my mentors, Christian, Mark, Steve, and Günther, as I am indebted to my collaborators and friends, Tamas, Randy, Jens, Heiko, Stefan, Annette, and Martin, to just name a few, seen here. Many of them are here today. I'm extremely grateful to the many fantastic fellows, the ones most contributing to work summarized today are Paul, Kerstin, Diego, Junsha, Ruben, Christina, Kirk, MJ, Christopher. There are so many more that not even this list does any justice. Thank you all. But I'm not done yet. But most importantly, I want to thank my parents who are watching the broadcast of this at home, and my wife Susanna and our children Franziska and Karl, whose love and support have been carrying me through the days where science life was less blissful than it is on this special day. I'd like to use the opportunity, though, to apologize to Franzi and Karl, as, you know, with Susanna also being a professor of medicine with a focus on diabetes and lipid disorders, these two obviously never have been allowed anywhere near sugar and fat-rich diets. Let me finally assure you that I was trying to do my very best today to give you a balanced view of the current landscape without being too excited about dual and triple receptor agonists. And as there won't be another version of this 12 years from now, I can once and finally say this: you stay classy, San Diego.
Thanks for attending the session. Please enjoy the rest of your day at the 83rd Scientific Sessions.